Hi everyone and welcome to Absio. Today we're going to be going over what Absio is and how it can benefit your organization. Now, the Absio SDK, generally speaking, provides low-level cryptographic functionality as well as some higher-level abstractions that make it very easy to natively add data security functionality to your application. So the Absio libraries are available in a multitude of languages, including C#, JavaScript, Java, Swift, and later this year, C++, and finally, Python 3, which is what we will be showing here today. Now, very high level, what the Absio library can provide is those cross-platform OS-independent cryptography, allowing you to do distributed key generation, very easily create secure messaging and key exchanges, individually encrypt some data objects, and the best part is you don't have to be a crypto expert to get all of this done. Now, individual docs are available at docs.absio.com for the specific libraries that you're interested in, for the different languages, I should say. And then Python specifically is available here at absio.readthedocs.io. So let's go ahead and jump in. We're going to start by importing the Absio library. Now, if you don't yet have it, it is available over here on pypy.org. Just type in Absio, search for it, and grab it here. There are some installation instructions for how you could go about actually installing it. We recommend doing so into a virtual environment. So we're going to begin by importing the library. And once that's available, we can hop into those low-level crypto primitives, of which we're going to be building upon these things to generate those higher-level abstractions that make it significantly easier for you. Now, the basis of everything that we do involves elliptic curve cryptography, and to get started with that, we need to generate a private key, and we can simply do this by calling absio.crypto.p384.generatePrivateKey, and that will give us an elliptic curve private key. Now, what can we do with those private keys? Well, typically, we use those private keys when performing ECDSA, which is elliptic curve digital signature algorithms. This allows you to prove the authenticity of a message or piece of data. And what you do is you take that data, you sign it with your private key, and that gives you out a signature. Then, given the public portion of that key, which you can distribute freely, if you then take that data with the signature and the public key, you can verify that in fact it was signed by that private key. So we're going to begin here by taking some random binary data to be signed. We're going to generate a signature by calling absio.crypto.ecdsa.sign, provide that private key that we had generated along with that data, and we can see that it gives us a binary, gibberish, random looking thing that is our signature. So now, taking the public key associated with that private key that we had generated, along with our original data and that signature, we can verify that in fact that data was signed by that private key. And by executing that line of code and not seeing that anything happens, we know that it was in fact signed by that private key. Now, if we were to modify either the public key, the data itself, or the signature, we would expect that this function would return an error. And in fact, it does raise an invalid signature error. So we're going to go ahead here and generate a new private key, take the public portion of that, so now we're validating with something that is not the public key associated with our private key, and we can see that it did in fact raise the invalid signature error. And in this case, we're going to modify the data by just reversing it, and in fact, there we have it, invalid signature as well. And finally, we can modify the signature by reversing it, and we have a invalid signature again. Now, the next thing that we can do with our elliptic curve private key is provide that over to a Diffie-Hellman key exchange. So that's ECDHE, and this allows us to share a key, or could be used to derive another key as like a shared secret that then is used to derive yet another key. This is very easy. Absio.crypto.ecdhe.exchange. You provide your private key, and you provide the public key of the recipient with whom you would wish to exchange with. And we do that, and it generates us out some random data. Now, chances are, if you don't know what this is, then you're not going to need it, and it's just important to be aware of it because the higher level primitives that we're going to talk about later have built upon all of this functionality. Now, moving over to symmetric encryption, we have everyone's favorite AES 256, and it's, again, very easy to hop right into this. To get started, much like with the elliptic curve portion, we also need to generate a key. And so with absio.crypto.aes.createKey, we will receive out an AES key. And from there, we also need to create an initialization vector. So let's go ahead and do those two things. Now, AES is most commonly understood to encrypt and decrypt some data. So we will do that. We will do AES.encrypt of some very important random data, providing in our AES key as well as that initialization vector. And then we will turn around and we will decrypt that encrypted data with our AES key and the initialization vector. And at the end, we should assert that our decrypted data matches our original very important data. And sure enough, it does. Now, one thing I haven't mentioned about the Absio libraries is that they are FIPS compliant by default. So that is FIPS 140-2 compliant. And with that, we are able to do hashing very simply. So absio.crypto.hash.getHash. This will generate a SHA-384 hash by default. Of course, you can modify this to specify other algorithms, but if they're not FIPS 140-2 compliant and the library is in FIPS 140 mode, then it would raise an error. So just something to be aware of. Now, combining the hashing as well as data integrity checks and authenticity, those things that we had covered before, we can move into HMACs, which is hash-based message authentication codes. So with this, we have to begin by generating a key that is suitable for HMAC SHA-384. And this is very simple by, again, just calling absio.crypto.hmac.generateKey. And that will give us out, again, some random binary looking stuff that happens to be a key suitable for HMAC operations. So now we have a bit of critical data, and we would like to generate an HMAC. How do we do that? Well, we just call absio.crypto.hmac.digest, providing in the HMAC key that we had just generated, along with this bit of critical data, and it will pop out a digest. This is very similar to the ECDSA, where we have a signature that is generated. But with this, it combines the authenticity check as well as a data integrity check all into one routine. So now we can call absio.crypto.hmac.verify, provide that HMAC key along with our data and the digest of the method. And because it did not raise an exception, we know that it was successful. Nothing was tampered with, and it was in fact created from the HMAC key. Now, if we were to modify one of those things, so for instance, we're just going to reverse the data here, we would see that the invalid signature is raised and we have an HMAC failure. So that's it for the very low level primitives that the Absio library exposes and makes very easy to use. In the next section, we're going to talk about the Absio integrated encryption scheme and how that builds upon those features to make your life easier. Stay tuned. Thanks.